Okay, I think that we can officially start. So before we start, I would like to introduce myself. My name is Maria, and I'm very honored to be your host today. I'm a partner engagement executive at Knowledge Point, and joining here with me is our industry expert, Cengiz Kurtoglu, who is a mechanical design engineer. Today, the topic for this webinar is mechanical simulation and analysis application in Autodesk Fusion, focusing on a comprehensive comparison of static stress analysis for a bracket design. Before we jump into the webinar and what we're going to talk about, let's look at the agenda first. So we're going to pick up on webinar highlights, a quick overview of what you will learn. We're going to say a few words about our partnership, the Knowledge Point and Autodesk partnership. Then I will hand over to our expert, Cengiz Kurtoglu, who will share a little more about what this webinar is today. Next, we'll talk about the upcoming webinar, which is webinar number 5, and we'll finish off with your feedback, and if you have some questions, to contact us and also share your thoughts. So as per the agenda, let's talk about the webinar highlights and what we're going to learn here. So today on this webinar, we're going to explore mechanical simulation applications, analyzing their impact on product design through a bracket design case study with pre-finalization revisions. We're going to focus on how to build an understanding of the simulation study types available in Autodesk Fusion. We're going to explore a bracket design project case study, revision of a final product as a result of static stress analysis, and we're also going to see a demonstration of the thermal stress simulation of a light bulb project. Before I hand over to our experts, I would like to say a few words about the Knowledge Point and Autodesk partnership. So celebrating years of excellence, Knowledge Point is the exclusive distributor for Autodesk learning in the EMEA territory that we work with. Our services offer a lot of them, such as print and digital support, highlighting our commitment in top-tier educational resources. As Autodesk learning partners, we uniquely enable essential skill development for leveraging Autodesk technologies. Now, I'm pleased to hand over to our industry expert, Cengiz Kurtoglu. The stage is yours.
Thanks, Maria. Hello, everyone. I'll start to share my screen first. I think it's okay. As Maria said, today we'll start with the subjects of mechanical parts in especially simulation of these mechanical parts and analysis, different types of analysis for these mechanical parts. I'll start with the present myself. My name is Cengiz. I'm working with the Autodesk as an authorized instructor for 3 years, and I'm a mechanical design engineer. I'm currently based in France, and I finished my university as a bachelor degree in Turkey, Istanbul, Marmara University, and I'm holding the diploma master degree in INSA Rouen, and I'm currently working on a research projects in the field of soft robotics, and also you can check it out, Design Wagon YouTube channel and Instagram channel. Today, in this webinar, as always, I'll explain different types of tools on Autodesk Fusion. We'll make a quick intro, and then we'll be focusing on the types of simulations in Fusion. There are several different types of analysis tool in Fusion, and you don't need any other software to make to solve this analysis. And I'll create a 3D design in the design workspace, bracket design. Um, After that, using some technical drawing, after that, we'll create an analysis for these mechanical parts in this webinar. For the projects, you'll see the static stress analysis of mechanical parts, and also we'll check it out thermal stress for a light bulb, or shape optimization, topology optimization for a mechanical part. And also, it will be nice for you if you are interested about analysis, simulation on Fusion. There is a comparison to compare two results or three results of your simulation. For example, static stress analysis results will be compared on the same projects. Well, let's make a quick intro for Autodesk Fusion. As you know, Fusion have different types of extension, different types of workspaces. Um, for example, you can access to create mechanical parts, and also form modeling tools on design workspace or sheet metal tools. After that, this design model, you can pass to, for example, manufacture of your parts using some 3-axis milling, 5-axis milling, or additive manufacturing tools. Or as today, we'll check it out, the simulation parts, simulation workspace on Fusion. Also, there are several different types of workspaces, like electronic drawing, like nesting, like manage, or generative design. Let's look at a design model. In the design workspace, you have access to create solid parts, CAD modeling, computer-aided design modeling, as you can see in the first part, table-wise mechanism. You can create using some sketches to obtain these parts, and on the same workspace you can access to um, assemble these parts. And also you have access to T-spline models for modeling or mesh modeling. If you have a 3D scanning, you can create your 3D parts after you scanned your parts. Especially, for example, prothèse designing will be the interesting for these mesh tools, or sheet metal tools. There is an example of a robotic arm. If you want to check it out, our first 3 webinars, we created these parts, these assembles on our first 3 webinars. And also in the render workspace, you have access to create high quality images and animations on Fusion. You don't need to change the software. You can access directly to create appearances on your parts on the render workspace for high quality images and animations. I want to give you a tip about the render workspace. If you want to create animations for your assembled parts, you can create a motion study for your parts, and after that you have access to render these motion study analysis. Motion study, for example, for these table wise, we already created all these parts on the design workspace and assembled on the design workspace. And if you want to create a render animation, just you can pass the render workspace and you can render it directly using motion study icon. For the animation, it's a different types of approach to create animation. Frame by frame, you can animate your camera angles also. For this robotic arm gripper part, for example, uh, it should be a component for these different types of parts. And then eh, if you want to create uh, this movement of the for this robotic arm gripper, you have to rotate all the gear parts and the other necessary parts. And today we'll be focusing on the simulation analysis. Let's check it out, the different types of simulation. Static stress. Static stress, it could be analyze the deformation and the stress into the model that you created on 3D workspace, design workspace, from a structural loads and constraints. It's very, very important to adjust, to assign your constraints for the all types of simulation, because to create a results to solve a analysis, it should be a loads or constraints for the parts that you want to solve. And after that, model frequencies, you can access to find the nodes for your parts that you created. Electronics cooling, you have access the electronic coolings on the simulation parts also. Thermal and thermal stress, structural buckling, and nonlinear static stress, and also event simulation. We'll check it out, these type of analysis. Dynamic event simulation, shape optimization, we could say topology optimization. It's well-known approach to lightweight your parts as a shape optimization, and injection molding simulation. Well, there is a result of static stress simulation of robotic arm gripper holder. As you can see in the displacement part, in the displacement results, the load will be on the rectangle of the inner parts of the servo motor, which is holding the gripper holder, and all the arrows, which is demonstrate the loads for the rectangular parts. And as you can see, the end of the part, maximum displacement, which is on the results of this simulation, the end of the part there will be the maximum displacement. We'll check it out in Fusion directly. And also there is a manufacturing workspace on Fusion, computer-aided manufacturing, CAM module. For example, there is a 3-axis milling, and also additive manufacturing, FDM, fuse deposition modeling. You can create your parts, you can assign your types of manufacturing tool, and then you could create your G-code to send to your machine, the manufacturing machine manufacturing tool. As a drawing, technical drawing, we already discussed on our last webinar, technical drawing. As you can see, you can create your technical drawings for your parts to explain the manufacturer for the all necessary dimensions, um, which is quite important. The title block explain the components for the drawing parts. On the other hand, you have access to create 2D or 3D PCB documents. For example, air quality sensor on Fusion. And the interesting part for this electronic design tool, you created the electronic designer created these parts, these 2D PCB, and then Fusion uh, create these 3D PCB documents directly. It's because there is a library for these all components, and it's automatically creates these 3D PCB. And then for a mechanical designing team, um, we'll use we can use directly this PCB design for our projects. And also generative design. Um, as we talked about the topology optimization for lightweight the parts, generative design uses the AI, artificial intelligence, different types of algorithms to create your parts just using some parameters as materials that you want to use on the projects, or the loads or constraints or the types of manufacturing tools. Uh, it could create tens of different results of for your projects, and then you can choose one of them, and you can also modify uh, for for these parts after it created these 3D results of parts. And now let's look at the modeling techniques in Fusion, and we can pass to simulation analysis for the parts. Well, we already discussed about the you can access Autodesk Fusion directly on your web browser, fusion.online.autodesk.com, and then you can access for all projects on your web browser. You don't need to download or install the software to your computer, or the computer doesn't need to lots of hardware for to solve the simulation, because to solve the analysis uh, in general, we need to lots of RAM, lots of hardware on the side of the computer. But using Fusion, we use the power of the cloud system. And now I'll show you directly using fusion.online.autodesk.com, and you have access for all your projects, and will generate a new type of simulation, and will solve the projects. Well, I'd like to start with the titanium rod. And normally the titanium has a, as you can see, the it's very strong material. It's not a cheap solution, but as you can see, you can after you pass a load on the material, different types of materials, it could be crack, or it could be um, the yield strength. It depends on the material. As you can see, the titanium has a great response for the load. Well, I like to start with the constraints on the simulation. As you can see, the constraint you can uh, if you select the C key for the on the simulation workspace, you can directly to assign a constraint fixed parts. As you can see, the end of the road in this side uh, for this phase, it assigned as a constraint for fixed x, y, z axis, and then there is a load here for the edge of the part. Um, and after this solution, it depends on the materials. You can change the materials, and the results will be different. But the logic of the simulation, it's always the same. If there is a constraint here, if there's a load here, the results will be for the linear parts, something like that, displacement, for the displacement results. And there is a probe to explain minimum value for the displacement and maximum value for the displacement as a millimeter. Well, if we change the constraint, the face of the constraint, as you can see, the same road, same material, but it changed the constraint phase, and also the load. So the result is dramatically different. As you can see, there is no changement on the load. There is no changement of the magnitude of the load. But here, the results maximum displacement 0.01 millimeter. But here, it's 21 millimeter. As you can see, if we change the phase of the constraint and the point of the load, the results will be changed. So in the simulation, uh, the important thing to assign the point of the constraint, first of all, and then assign the load, uh, point of the load. After that, it will be fixed. So we can change the design of the parts. Now, I just want to um, um, the um, the question about these parts. If there is a foresight fixed as a XYZ fixed in this part, in this basic rectangular parts, and there is a hole inside of the rectangular parts. Well, and also, as you can see, there's an arrow, there's a load, which is assigned in the inner hole of the parts. It's not important the material. It's not important the what kind of load or what kind of magnitude for this load, just the logic of the simulation. If there is a four side of the fixed, and the what is the results for these parts? There is a response. The maximum is depend in material used. Yes. And if you think about what is the um, um, geometrical result for these parts, for example, if there is a load on the center of the parts, and if there is a foresight is strict, is fixed, and the results will be here for the displacement map, for example, because um, foresight is fixed. It couldn't be moved normally, but in the center of the part, there's a load. So uh, the um, the the displacement results will be the maximum in the hole directly. So if we change the approach, if the constraints are the same for side of the parts where the x, y, z fixed, but on the same uh, inner face of these parts, but the load is changed. Load is not the opposite of the whole axis. It's directly to the forward and on this, as you can see. So what will be the results for this part? Well, we'll check it out together. As you can see, there is an elliptic results in for this basic simulation results, because for this load in this direction, in this axis, there's uh, a force, a load. So it's not very important to right and the left side of these parts in these conditions, but the important parts in the load will be this direction. So as a result of on the same condition, the load direction is changed and the results are also changed. Well, for the same part, we change the constraint. Well, if you think the constraints here, the whole is constrained. It doesn't move on the center of these parts, but right, left, and forward and backward, all faces, uh, there are loads on the four side of the this rectangular part. What will be the results? What will be the most maximum displacement on these parts? Let's check it out together. Well, as you can see, the displacement is minimum on this side, and the maximum displacement in the edge of these parts. Well, because there are two side of the load, and also the um, uh, the parts, the different size of here. For example, in the diagonal way, there are more longer here. For it could be more results um, as a maximum value in displacement. Well, it's just a explain about the basics of static stress simulation. We'll see these parts to compare two different uh, bracket design uh, to solve these parts, as you can see, there are two different design, and the results are changed. If there is a rip design here, the safety factor will be the focusing on the rip. But if there is not a rip design, there will be a fragile in this zone, especially here, because there's a constraint here in the XYZ, and there's a load for this circular tube. So there's a good example for explain the static stress simulation. Let's see the results of the second analysis. As you can see, in this side, there is a long um, fragile region here. But if we create a rip design, it will be changed. So let's check it out, and let's create this part on Fusion. Before that, I'd like to explain the mesh. As you can see, there are triangles on the parts, which is called nodes, and we generate mesh for the parts that we want to assign a simulation solution. It's very important. And also, if we want to analyze a part, it should be a mesh. It should be generated a mesh for the parts. There's an approach if you want to uh, results, a good results, a fine results. You need to change the value. You need to maximize the number of the mesh numbers. But if you want to just check it out results quickly, you don't need to create lots of numbers of mesh, because Fusion or other softwares, their respects to all the numbers of mesh, and they'll solve for each of them meshes. For example, there's a materials specifications, there's a constraints for all of the meshes, there's a load on, and also in these conditions it will be different conditions. Uh, it has to solve for each of them. So let's create these parts on Fusion together. Well, I'm switching to Fusion. As you can see, the numbers of these parts, it's not a millimetric, it's a inch. So we need to change the um, dimensions, numbers on Fusion. If you are using a millimetric metric dimensions, we can change together. I'm also using the metric on Fusion. But if you are using inch, you can use directly for these parts. And as I told you in the beginning of the webinar, I'll use web browser because in general, on simulation, we need to solve these parts, more powerful hardware, but now on Fusion we have access to web browser directly to create your parts as a design, as a manufacturer, as a render, as a simulation, whatever you want. It's very handful, and on simulation, normally before 5, 10 years, it was a dream to create the to solve these simulations on a web browser. But now I just I mean I'm using a normal PC. There is no workstation here, so let's check it out, the results of this simulation. Um, I'll start with designing the parts together. Well, let's start with the create sketch, X and Y axis, and I'm selecting R. Normally the 2-point rectangle, but I'm using center rectangle. Now it's asked me the millimeter, and I forgot to switch to document settings. Let's change the millimeter to as a unit type inch. Let's say okay, and it changed. Now I'm creating a sketch here, R, center rectangle, and then let's create a rectangle, and then we'll we'll I'll I'm pushing D button here, 5.5 normally, but if you want to enter 5 plus 1 divided by 2, Fusion could compute the basic mathematic um, examples. As you can see, 5 plus, sorry, 7 plus 5 divided by 8. And now we created our first rectangle here. And I will look at the, normally I created the 7 plus 5 divided by 8 and 5.5 here. And then we'll look at the 1 plus 1 divided by 8 to create the extrude. And if you want to create the holes here, you can. Let's create our holes here, because there's a hole as a diameter 2 plus here. I'm selecting C key here. 2 plus 5 divided by 8. There's a hole. And if I push the shift button, push and hold, and selecting origin, we can assign a constraints here, or just right click and horizontal vertical. That's great. And then there is a 5 millimeter here, 5 millimeter in the technical drawing. So we can pass to 1 as an extrude for these parts. I'm pushing E button. 1 plus 1 divided by 8. And then let's create these parts. And as you can see, there is a second circular uh, pattern here. Um, let's create the diameter. I'm looking at the diameter 4 plus, let's create a sketch here, C. It will select the origin 4 plus 3 divided by 4. And now, as you can see, and then there's a explaining here 1. Let's write it down in the parentheses to get the results. 1 minus 1 divided by 2 and minus in the parentheses 1 minus 1 divided by 8. Well, I'm changing the minus because it should be plus here and here. And then we can change the operation as a join. It's okay. As you can see, we created the parts. And now let's create these two circle here, and there will be a line as a tangent. There's a point 5 plus 3 divided by 4. Let's create from here C. Well, there's a circle as a 1 plus 1 divided by 2. And then D. Five plus 3 divided by 4. L. And then there's a second circle 3 as a dimension. Now it's important thing to assign a constraint as a horizontal. Let's make a horizontal for these parts, and second one full constraint. That's great. Now we have to create two lines for as a tangent here. You can catch the tangent from here and here. That's great. And now let's start to make the extrude for these parts. Well, here, both of them, sorry, and minus 3 divided by 4. As you can see, we created the side of 3 divided by 4 as a join. That's good. Okay. And now, after you used a sketch in the previous step, you can go back to sketch as for example, sketch 4, because we need to continue for our parts, because uh, we can use our parts to create to new tube here. But now I just want to show you a trick for these parts. As you can see, there's a 1.5 extrude, but the sketch should be in the mid plane for two sides of the faces. Now you can use the construct as a mid plane here and here. As you can see, there's a mid plane in between the two faces. I'm selecting OK. And now I'm creating a sketch directly to, I'm pushing P button. P is a project. In the project, I don't want to bodies. I just want to these two circles, because I just want to need to use these circles, but in the mid plane of these two parts. Now I'm selecting E key. As a result of the direction, we can select it as a direction symmetric. And the symmetric, there's a measurement, half length or whole length. So whole length will be the answer for me, because distance in total distance, 1 point plus 1 divided by 2. So as an operation, join, that's all. As you can see, we created our parts as mentioned here. So there is a rip here, and also it didn't mention the radius, but you can use F key as a final parts. For example, 1 will be the nice for these parts. Well, we created our parts. That's okay. Control S, you can create new projects for these parts, or as a location you can select for your projects. For example, CAD simulation 01. Well, I saved the part, and after you finished the modification for your parts, you can pass to simulation analysis workspace. In the first place, as a new study, static stress, let's create study. And also, if you select this little icon here, you can access the settings. If you want to change the name of your first simulation, you can enter, or you can assign your settings for your mesh. Model base size, it depends on your model. It could be a 10 millimeter or 1 meter. Um, it it depends on your it based on your model size, and 10% of your parts will be the triangles for your mesh. Um, if you change to do 1%, it will be the tiny little lots of mesh on your parts, but the results, the the generation of your mesh, the time will be the increase, and the results to solving your analysis, the time will be the increase. And also you have access to advanced settings for the mesh. If you are researcher on the different types of analysis, you can change the settings for your parts also. Adaptive mesh refinement, you can change as a default for your refinement control. But now I'm changing nothing as a basic result for static stress, create static. Well, um, as a user of Fusion or all of the part of all of the software or of Autodesk, the same logic will be the help you. We are starting to the left and we are going to the right. Simplify, it depends of your parts. For example, there's a fillet here. You can erase your details for your parts to simplify because the mesh uh, generation could be difficult to create a little triangle here to assign mesh will be the difficult for here or I also used simplify as a revise my parts. For example, there is a reap design here. You can go back to the design module, design workspace, and you can add a reap design here, or you can use simplify. You can add the reap design and you can create new results for your parts. Materials will be the uh, quite important to use these study materials because different types of materials respond different types of results for your parts. As a default, the simulation creates a design material steel, but you can change the study materials here if you want to change the materials. Also, you have access the material properties. If you want to check it out, your materials for example, aluminum, there's a Young modulus here and yield strength. And also there's a time to if you are using a custom materials, if you need to add different type of yield strength, for example, uh, you can change the parameters of your materials, manage physical materials here. You have access the library, Fusion material library here. If you want to create a favorite materials, you can. And also, for example, ABS plastic here. Uh, there is a appearance. Appearance, it's all about the render workspace. You don't need to change or modify appearance for a simulation analysis workspace, but physical properties is important for simulation analysis. For example, basic thermal, mechanical. You can change the Young modulus here, strength, can access the yield strength, tensile strength for ABS plastic, and also you can check it out the all parameters for the different types of materials here. And if you want to access the material model, for example, if you are researcher for a nonlinear static stress or nonlinear analysis, it could be interesting for the material model for a hyperelastic, for example, or a different types of behavior, linear or nonlinear. So I'll let you check it out in details for this material browser. But I also have to mention you have access all of them using fusion.online.com. If you are a researcher or you are going to different zone on the site as an engineer, you have access directly on web browser for these simulations. So as a material, I'll let the materials as a steel constraints, structural constraints here. Well, there's a different type of structural constraint. As a pin, for example, you can uh, select the targets as a radial or as an axial. You can change the different parameters or frictionless. You can select the zone as a face here, frictionless. Prescribed displacement, or remote. You can change, you can assign your structural constraint as a fixed. Also, if there is a three-axis fixed as a default X, Y, Z as fixed, or if you like to add or remove one side of the parts as a X, just Y and Z axis will be the fixed. So I quickly check it out our results. As you can see, you can change the theme from here. Let's save. And we have access all of the projects as a results and team. If you are using different types of team, you can change, you can switch between the team accounts directly. For example, as a single user for me, I'm uh, using my projects as a single user, and also I already participate different types of projects, different types of team, and we created um, different projects as a team for the parts. Well, uh, let's continue from here as a simulation. Well, there is a two different results, finished results. Let's continue from the materials. As a materials, it's steel. As a constraint, we already selected these parts, X, Y, Z as a face. But if you like to change or add different zone, you can add as a constraints, but uh, it doesn't necessary to add another constraint. It's just one, and it will be the nice for start your solution. Um, as a structural loads, it's commonly used loads as a structural loads, but if you need the linear or angular global load, you can add. And also gravity, you can add the gravity or edit the gravity. And point of mass for as a manual or auto, you can change. Let's check it out, structural loads. As you can see, the types are changing. A force, pressure. If you are selecting pressure, like here, the magnitude, the unit of the magnitude are changing as a megapascal here, or you can change the units as a pascal, megapascal, psi, bar. So if you are adding a moment here, Newton, millimeter, you can change the units here. And also bearing load, remote force, hydrostatic pressure, remote moment. Well, I'm selecting force. I just want to explain different types of approach for here, because as a direction, if you are selecting normal here, for example, um, the structural loads responds as a normal of the phase parts, phase. But if you are selecting angle, you can change the angle for X, Y, and Z. The magnitude will be the different for direction is a different thing, and magnitude is a different thing. But also, as a vectors, you can add um, as a Newton for the vectors, because the direction, for example, in the X, Y, Z, just 30 degrees and for example, 15 kilonewton. But you can add directly here different types of Newton. It depends on your projects, but you have access to direction type. So uh, there are also there's also an arrow here. If you are selecting arrow in a 2-click, you can edit your structural load. For example, there's a 45 kilonewton in the Fx here for the edge of the parts. So we already assign materials as steel, constraints here, XYZ, and loads. Now there is a tool as a contact, automatic contact, manual contact. Um, it it concern about the if you are using for example table-wise components, there are several components. If you are using several components to solve your parts, you can select the automatic contacts or manual contacts. And the display, there is a toggle mesh visibility. As you can see, if you are uh, pushing E button, mesh is a 10% model-based size. If you need to more detailed mesh, you can add it to push the icon, a little icon here. For example, I'm changing the parts, and you have to need to generate mesh to assign the new settings of the mesh. And also you can access to E-key settings here, and also local mesh control. For example, you need to more mesh results here. You can change the length for this phase to change the results for the mesh assignments in this phase. So after all finished for your sites, you can quickly check it out, ready to solve. The study setup has all the information required, is okay. And then you can push the solve button. As a result, for example, here. Well, I just want to explain the tools that you can use here. First of all, you can change, you can access different types of results. For example, here it starts with the safety factor. You can change the stress. In the stress, you can change the as a one misses, a shear, a normal. Also displacement, for example, is a maximum points 12 millimeter here. And also it's important because front, as you can see, there's a huge displacement here, but you can change as an undeformed. You just, if you just want to see the legend and no displacement, no changement for your parts, you can select the actual or undeformed or adjusted. It's changed. It's changed the approach the part to. For example, here it's 5 times bigger. If you are selecting actual, it's 12 millimeter. Okay. Well, reaction force, different approach and strength. I just want to show you a legend here. For example, after 500 megapascal, as you can see, there the parts is a fragile here as a stress. And also in the displacement here, safety factor here. So if we add rip for these parts, well, let's compare the results. For the study 1, there's a rip. As you can see, the safety factor is changed, and also the result of the red parts, red region, is changed because the new design it absorbs the all load and constraints for the on the rib parts, on the edge of the rib parts. So it could be more reliable to add the rib design to enforce these side of the parts. As you can see, there's no big issue for the two side of the parts. Let's compare together on the one page. You can change the browser here. As you can see, for the first part, there's a rip design here on the safety factor, and the second, there's no rip design. So the results are explain us to changing the parts as a design tool using the rip design here. You can compare, you can animate your parts. For example, here, you can change the step for T, for example, and fast, two-way. And after that, you can record as a MP4, and you can add your presentation to explain the your client or jury. So let's switch the other parts. If you want to create the rib parts, also I just want to mention you can create a sketch here in this axis and just a line, just a 2-point line here and here, and that's all. There is a tool as a rib and the dimension for this extrusion to whole length 3 divided by 4h. Well, as a different analysis on fusion, thermal analysis, for example, let's check it out. Thermal analysis on fusion. Um, as you can see, there's a light bulb design here. Um, let's change the as a heat flux. Well, I just want to explain quickly the materials. If you are selecting materials, you can have access to all components. For example, here, there's no one parts. There's no one component. There are several components. For example, base, steel. Second one, heat sink, brass. There are lots of aluminum parts as a heat generator here, copper as a driver, and the panel is aluminum. So you can change the components, but it's important as a result to assign exact materials that you are using on the projects. After the materials, you can pass the loads as a thermal loads, or you have access here directly, study materials and loads case, loads, internal heat. So the diode as an internal heat, we are selecting for bodies as a type of internal heat. You can change as a heat source or radiation, convection, applied temperature on the thermal loads. But um, here we already selected internal heat as a 25 watt. You can change the units if you need here. And after you assign thermal loads, there's a convection here to assign a type of convection value, watt divided by meter square Kelvin, 100, and also ambient temperature of the zone, 25 Celsius. And for this project, the important thing is, as you can see, there are several patterns. If you are changing, if you are modify the design, the results will be changed dramatically. Well, let's check it out. Before that, you can check quickly the mesh results. As you can see here, all generated as a mesh. Well, let's check it out. Results here. We have results. As you can see, heat flux here. It's beginning from the diode, and it's continuing gradiently to the all parts. If you are changing the thermal gradient, you can, as you can see, it's all on the top of the parts. It's the beginning of the heat source here. The temperature, it's quite good. Gradiently, it's changing here, as you can see. Well, if you want to change the parts here, for example, you can create a clone, a new clone, and you can change the erase the parts here to simplify, or you can go back to the design, and if you want to change as a for example, there's a 14. Let's change to 4, the part, and I'm go back to simulation. Well, as you can see, the results will change. Yes, I know it's not a big deal. We'll check it out, the convection parts. Before there's a um, lots of faces, but now there's just here, and then it's okay. We are assign a new mesh for these parts because design are changed, design are modified. So um, we are creating a new generation of these parts, and for as a mesh, it will create a new mesh, and then we'll pass to check it out the results here. Let's continue on our presentation. And also there is a topology optimization on Fusion. As you can see, shape optimization. There is a load here, and the two parts are fully constrained as x, y, z fixed, and there's a target percentage. For example, 35%. I'm looking for lightweight result for this part because in the results here, blue zone, it's not necessary, quite necessary for durability for this part because there is a force here, the important part here, in this zone and there. So if you want to modify, raise some parts for these projects, we can start to change the parts here. Well, as you can see, the results. And after that, uh, we can access to uh, create, promote these parts. The all zone could be the mesh, and we can modify our part directly on design workspace. I'll show you on the well, as you can see, light bulb, it's generated, it's all done, right? And now um, in the solve section, pre-check, it's okay. Solve. Let's solve this simulation. In my account, it's not a contract for this simulation. Well, I'll show you on my on our next webinar to results of these parts. But also, if you want to check it out, these results, you can create your parts, because for this light bulb, you have access this design here on your Fusion projects. There's a simulation samples. You can find the part on the Fusion simulation folder. Well, I'll show you quickly topology optimization part to create your own parts as a simulation. Well, the logic is the same. We are assigning materials, load, constraint, and also shape optimization target body, shape optimization criteria. Well, for example, it's 45% as a unit. it tries to lightweight your parts to 45%. It's quite interesting for as a shape optimization settings. Well, let's quickly check it out, the results. Well, you can change here for the first ratio as a shape optimization. You can change the target here 45 percent mass ratio, and approximately mass is for example 70 kilogram here, but first in the first is a more the of 150 557 kilogram. It changed, and after you find your target body, you can select the promote, and you will switch to design workspace as a mesh body here. You can have access to the mesh body, and you will have access to create your own parts, to modify your parts. Well, let's continue on our on a different projects for a front holder, uh, front loader here. There's a project to create a new parts or lightweight the parts, uh, to comparison between the generative design setup and shape optimization setup. Well, I'll explain the shape optimization setup in this webinar, but the next webinar will discuss on generative design setup, because you don't need to create starting shape for a front loader. But as a shape optimization setup, you have to create your whole parts. After that, we are trying to lightweight the part, but as a generative design creates new parts and don't need to first 3D mesh. Well, as a result of topology optimization for front loader component, as you can see, for the three zone, it's in the path is a critical, but the transparent part, it's not quite as a safety factor. It's not quite important. You can erase these parts from here to approach to create a more lightweight parts as a front loader component. Uh, on the other hand, as a generative design solution for front loader component, as you can see, we can select different types of manufacturing tools. For example, here as a stainless steel um, two-axis cutting. Uh, we already selected our um, parameter as a manufacturing method, two-axis cutting, and it created a part using some AI-powered algorithm. And as you can see, there's a result for front loader component. But on the topology optimization, we already created our part, and we have to modify our existing parts. But on generative design, you don't need to you don't need to design a part. Just explain the parameters, and then Fusion creates new parts as you want as a parameter. For example, in the manufacturing method, 2-axis cutting here, and also 3-axis milling. Same part, same dimension for the shaft for the milling here, as you can see. But the in between the parts, in between connecting zone, they are changing because the generative design algorithms, it's find the solution as you want. There's another example for a event simulation axe shop. As you can see, you have access the dynamic simulation on Fusion also. If you want to check it out, you can go to the control panel simulation and you have access these type of examples also. Well, as I mentioned on our next webinar, webinar 5, um, we will be discuss about the generative design technology. It's quite interesting, lightweight design of the vehicle suspension control arm, for example. And I'll show you um, the difference between the topology optimization and generative design. It also interesting to find the differences between the generative design and topology optimization because generative design don't need to starting shape, but you can also assign a starting shape if you want, but it doesn't necessary, it doesn't mandatory, uh, and generative design respects the manufacturing method, for example, 2-axis cutting, additive manufacturing, 3-axis milling, but topology optimization doesn't taking into account the manufacturing method, the important differences between two technology, two analysis. Well, I'd like to thank you for listening. And if you have a question after this webinar, you can send me a mail or you can check it out our YouTube and Instagram account as a Design Wagon. Well. I'll pass to Maria for the
Well, I'm going to start by saying thank you. I would like to share my screen. I think that this was a very informative and valuable expertise from your side. So again, thank you. And I hope that all of you learned something from this very informative webinar. As Genghis mentioned, and basically he covered most of what you're going to listen and learn in the next webinar. The next webinar is webinar number 5 in our series of 6 webinars. We're going to be revealing the generative design technology in Fusion 360. We're going to explore the world of lightweight vehicle suspension control arm design. The next webinar will be held on January 24th at 5:30 UK time. Also, don't worry, the recording of this webinar will be shared afterwards, so you will all have it, so don't worry. And if you have any questions and feedbacks, please email me and contact me whenever you want to on this email that you see on the screen. I would like to say thank you to all of you who attended today. So take care and have a wonderful day.
Thank you. Have a wonderful day.
Thank you. Bye.
Bye.